Hello, welcome to Unit 5, Lesson 11, Modeling Exponential Behavior Video Notes. In this lesson, the learning objectives are you will be able to use exponential function to model situations that involve exponential growth or decay, and you will be able to determine an appropriate model for the situation described by the data when given certain data. Alright, we are going to go ahead and skip the first activity and move on to activity 2. So in this activity, we're looking at different measurements of the maximum height of a tennis ball after bouncing several times on a concrete surface. So imagine you took a tennis ball and you just bounced it once and let it continue bouncing without catching it. So this table shows the number of bounces and the height after that bounce. So for example, the height before you bounce it is 150 centimeters. And then after the first bounce, it's 80 centimeters. After 2 bounces, it's 43, and so on and so on. So question 1 asks, which is more appropriate for modeling the maximum height h in centimeters of the tennis ball after n bounces? A linear function or an exponential function? Use data from the table to support your answer. So go ahead, pause the video, analyze the data, and see if you can come up with a good response. Alright, let's take a look at the data a little bit more closely. So we see that it starts at 150 centimeters. And then the bounce after the first drop is 80 centimeters. Now, if I wanted to see if this was a constant rate of change, I would calculate the slope, right? If I wanted to see if there was a growth factor, I would see what fraction is remaining each time. So you kind of have to take a look at each type. So for example, if I looked at constant rate of change, okay, between bounce 1 and bounce 2, that would be the difference of 150 and 80 over the difference over 1. So the difference of 150 and 80 is 70, so that's 70 over 1. Between bounce 2 and 3, I would do the difference of 80 and 43 over 1, which would be 37, and then so on and so on. And then we've got 20 minus 1, or 20 minus 11 is 19, 9. Not 19. So we can see that the constant rate of change is definitely nowhere close to each other. Let's take a look at what the growth factor would be. So, or in this case, decay factor, but we can still call it growth factor. So remember, it's always a fraction of what's remaining. So for example, for my first one, between bounce the initial height and bounce 1, I would have 80 over 150, which is approximately 53. For this, between the first and second, I would be 43 over 80, which is approximately, again, 53, but actually if we round up, it would be 54. Between bounce 2 and 3, that would be 20 over 43, which is approximately 47. And then between the last 2 bounces, 11 over 20, which is approximately 55. So this one, we can see it definitely looks a little bit more consistent, right? The 47 is a little bit out there, but that's okay. But for the most part, they're all pretty close to each other. So based on that information, this tells us that the best model for this data would be an exponential function. And we can see that from the data, right? That the growth factor is a little bit more consistent than the constant rate of change is. Let's look at question 2. So question 2 says, regulations say that a tennis ball dropped on concrete should rebound to a height between 53% and 58% from which it was dropped. Does the tennis ball here meet this requirement, and explain your reasoning? Now, we already looked at the decay factor or the growth factor, whatever you want to call it, for this. And you really could make an argument either way, right? At first, it kind of does start off in that requirement. And the last one, we also see meets the requirement. There's really only one bounce that doesn't meet the requirement. So it really could go either way. All right, let's take a look at question 3. So this one says, write an equation that models the bounce height h after n bounces for this tennis ball. And there's a couple of different ways that you could approach this data. Looking at the different growth factors, right? We have a range of numbers, right? 53, 54. Oh, I just realized those should be 0.53, 0.54. Sorry about that. So it could be 0.53, you got 0.54, 0.47, 0.55. So it really does, it really could change. You could just say, well, they're all about 1/2 and go with 1/2. You could just use the growth factor of the first 2 points. You could also take an average of the growth factors and seeing that it's 0.53, right? You add them all up, divide by 4, and you get about 0.53. So really, it doesn't, because it's not a perfect situation, you have some options. So personally, I would probably go with about 1/2 because they're all fairly close to that number. So one equation could be h equals 150 times 1/2 n. But again, not 2n. But again, that you could also use like different numbers just as long as it's within that realm. Question 4 says, about how many bounces will it take before the rebound height of the tennis ball is less than 1 centimeters? So go ahead, pause the video and see if you can come up with an answer here. So you have a couple options. You could have graphed this equation in decimals and see where it crossed where the x value is 1 centimeter. Or you could take the idea that the ball is decreasing by a factor of about 1/2 each bounce. So if you go with that idea, you would see that after 3 more bounces, it will decrease by a factor of 1/8. And then about after 4, it would decrease by a factor of 1/10. So keeping all of that in mind, we would say that at about 8 bounces is where we would see it reach about 1 centimeter. So you have a couple of different options. So just keep in mind that, real world situations aren't perfect, right? They get a little messy. Nothing is set in stone. We've talked about this before, about how when we're looking at ideas of real situations, those differ than the actual mathematical perfection, I guess you could say. So Real world's a little messy, so sometimes you kind of have to take an average or a close estimate to really get a good representation of the data. And just like we've talked about before, technically if we were to graph this equation, it would never reach 0, but we all know that eventually a tennis ball is going to stop bouncing, so it would eventually reach 0, but that's just not represented mathematically. All right, so let's go ahead and take a look at the next activity. We are actually going to skip activity 3 and go to activity 4. So activity 4, we're looking back at the heights of a ball after a certain number of bounces again. So this time it does not give you the height in centimeters for bounce for where it starts and for bounce 1. So go ahead, answer questions 1, 2, 3, 4, and 5. 2, 3, 4, and 5 do go on to the next page. Pause the video and work on those. All right, let's go ahead and answer these questions. So question 1 said, is this ball more or less bouncy than the tennis ball in the earlier task? Explain your reasoning. So what we can do is try to figure out the exponential factor, or the growth factor, between bounce 2 and bounce 3. So to do that, you're going to do 51.5 over 73.5. And when you divide that, you get about 0.70. So based on this information, we can see that the growth factor is much bigger than the growth factor or decay factor in the previous tennis ball problem. So that tells us that the ball is bouncing higher than before. So it is going to be more bouncy. Okay, let's look at question 2. From what height was the ball dropped? Explain or show your reasoning. So for this one, if we're assuming the growth factor is 0.70, which is 7/10, to figure out going in the opposite direction, we always talked about how you can either divide by 0.70 or multiply by the reciprocal, which is 10 over 7. I'm going to go ahead and divide. So 73.5 divided by 0.70 is equal to 105. So this tells me after the first bounce, it was at 105 centimeters. Then I do that again. 105 divided by 0.70 is 150. So this is the initial height, 150 centimeters. Question 3 says write an equation that represents the bounce of the height of the ball in h in centimeters of after n bounces. So now that I know the initial height, I know my equation is going to be h equals 150 times 0.7 to the nth power. Question 4 asks which graph would be more appropriately representing the equation for h, graph A or graph B. In this case, we're going to say graph B. And the key word is appropriately, right? We could use graph A to represent this situation, but graph B is more appropriate, and that's because we need to keep in mind that the number of bounces can only be whole numbers. It can't be decimals or fractions. Graph A would show all numbers between 0 and whatever number of bounces, whereas graph B only shows the whole number of bounces. So this one only shows the whole number of bounces. So although, like I said, you could use graph A to represent it, B is definitely more appropriate. Last question. Will the nth bounce of the ball be lower than the nth bounce of the tennis ball? So if we think back to the tennis ball, we know that the tennis ball has a lower growth factor. So therefore, the height of this ball in this situation will not be lower than that of the tennis ball, because we're assuming they were both dropped at the same height based on what we found out, and this one has a greater rebound factor. So if we were to compare the same bounce for each ball, we will see that this ball will always be higher. So no. This ball will always be higher because it has a greater rebound factor. So if we think about it, this is probably something like a bouncy ball rather than a tennis ball, right? Bouncy balls, those little things that you can get out of like the machines at Walmart or something, those tend to bounce a lot higher than tennis balls. So that's it for this lesson. A few things I want you to keep in mind: that when you're dealing with real world situations, it's not completely perfect, right? Sometimes the data is not 100% accurate. Like with that tennis ball, we noticed we had one bounce that was a lot less than the other ones, and that could have been for a variety of reasons. They could have been measured wrong. It could have hit the floor in a funky angle. It could have hit something that made it not bounce as high. So it's not really perfect. There's always going to be some measurement errors there. Also keep in mind that when you're determining if it's a linear relationship or an exponential relationship, you really need to compare the rate of changes versus the growth factors or decay factors and decide which one's a little bit more consistent. Keeping in mind that there will still be some inconsistencies within the problem, but you just want to go with what's the best situation. So that's it for today's lesson, and thanks for watching.